for the next 2 weeks. Okay, so 2 weeks left of class. Almost done.
That include this week?
That includes this week.
Because you have final, that's why.
Yeah, no final. Which, yeah, first thing, no final. So just to counteract those questions. But we got stuff. So today I'm starting on AC circuits. I plan to finish it this week. Hopefully, it's a chapter. Expect a quiz over it on the weekend and the expert TA due on Friday. Next week we'll wrap up with waves. Again, that expert TA will be due on Friday and you'll have a quiz over the weekend. Okay. Things to say. That Friday, yes?
Are we also going to be presenting next week?
No. Okay, so the final day to turn in any work on the expert TA is December 9th. That's next week on Friday.
December what?
9th. On December 10th, I'm downloading the grades, and after that, I don't care, no more expert TAs accepted. The same thing for any late quizzes. So I allow, a 3-week grace period on the quizzes if you let me know. But December 9th is the hard cutoff. No late work after that. Your explain something revised slides. The final slides are going to be due Friday, December 9th. So first off, I'm going through the peer reviews. Has everyone got their peer reviews done? Thank you. Have you been able to access the reviews people left for you? Okay, sweet. Okay, so the final step here is now you're going to take your slides, you're going to look through your peer reviews and whatever you think, and you're going to do a final revision on your slides. I'd like to say that I know a lot of the advice that you're going to get from your reviews probably isn't going to be advice that you're going to follow, because just the people who reviewed your slides might not have the same vision for your project that you do. So, and that's totally fine. But I do expect you to thoughtfully look through their advice and revise accordingly. Yes.
So how about, so if I resubmit the same slides that I had for my peer review, would it be fine to, since my slides, I kept it pretty brief.
Okay.
Kind of vague, so I explained it with
Good.
verbal, so I didn't make it too brief. Part of my critique at the beginning was that it wasn't like, I guess, complex enough or something.
Okay.
Yeah, so should I just update the slides then, or should I just stick with my plan?
So the one thing I'm going to ask you to do is to add a final slide, just like at the very end, to say, I looked through the advice I was given, and this is what changes I'll be making. And so if that means that you're going to say more things during your talk, or hey, they said that I should explain this thing more, and they weren't sure I was going to because you plan to do it verbally. They're like, okay, I'm addressing this by talking verbally, explaining this concept. That's fine. Just as long as you say, I saw this advice and here's what I'm going to do with it. Okay, and so you'll see on the instructions even, it says add one extra final slide to your slide deck. Just here's the advice I got, here's what I'm going to do about it. And again, you don't have to follow all of the advice you got, just choose something that makes sense to you. If you got the same advice from both your reviewers, you should probably think hard about that advice. Yes.
So is the grades on iLearn, I'm curious, what's everything is graded?
Ooh, okay, let's see. The grades on iLearn are probably not, so I don't have the expert TA on iLearn right now.
Well, not what's everything's done, by next week, what's everything's in, would it be accurate, or what is it?
I would recommend checking your grades around the 15th or 16th of next week. They still won't be absolutely finalized, but that'll be pretty close. I would recommend just looking through the stuff that has been graded, and if you notice anything really just ridiculous, Like one thing that a lot of times happens with the quizzes is you'll see that you got a 1 out of 10 instead of a 10 out of 10. And usually that's just because someone didn't hit the 0. And so they meant to put in 10 out of 10 and they put in 1. So that's the sort of thing that you probably should like look back through your grades now and just make sure that the grades make sense based on what you submitted. Okay. So I was talking about the slides, revise them, add that final slide at the end, talking about your revisions. That's due Friday, December 9th, the last day of class. Then the time we have allotted for the final exam, which we don't have an exam, we're going to use to present. And you have a choice. You can come to class at 2:45 on Tuesday, December 13th and present your presentation. Or there's a forum online. You can just record a video of yourself and you can upload it to the forum.
When can we upload that?
And the due date is Tuesday, December 13th. Yeah, so your presentation is due either in person or recorded. You can come to class and just present it. You can record a video and put it on the forum. But December 13th is the date for that.
You said the video had to be at least 5 minutes.
You should aim for 5 minutes. I'm not going to take off points if it's more than like 7 minutes long, but if it's more than 7 minutes long, that's no good.
You said a minute per slide, right?
Yeah. If it's less than 3 minutes long, I will start taking off points then, because that's pretty terse at that point. But like if you're, but if you like 4 minutes, sure, whatever, 4 minutes. Okay. Yeah, it's okay. Okay, so that's that. Okay, I would like to emphasize that the presentations are either or. Either come to class or put them on the forum. If you do put the videos on the forum, I'm going to ask that you watch some of the other people's videos and make 2 comments. So reply to two other people's posts with comments about their slides. The comments will be due Friday, December 16th. Yes.
Can we upload a video for a class?
Yes, you may. Absolutely.
Do we have to do a comment?
Say again?
Will we still have to do a comment?
You would, because I'd have no way to track you. Yeah.
Okay.
So if I present, I don't have to do the slide?
Yeah, if you just come to class after December 13th, you are done. If you come to class. Yeah, you'll be presenting to these 3 people.
I'll probably be here, so.
Yeah, it's a pretty straightforward. And then the last thing on this project is there's a reflection essay, I think 300 words, like 1 page, what you liked, what you didn't like, what you would change, and do something for each of those.
For the course?
For the presentation, for the project. So that's going to be due on iLearn Friday, December 16th. And yeah, even if you hated every part of it, find 1 thing you liked. And even if you loved every part of it, find 1 part you didn't like.
Okay, so this is December 12th.
Yeah, well, that's due December 16th.
I mean, our.
Yeah, the December 13th, that's the Tuesday. 2:45 is when I'll be here. I'm not staying till full 45. If I show up at 2:45 and no one's here, I'm going home. Yes.
That's our presentation day, right?
Yeah. And then the comments for the forum and your reflection essay, December 16th. Okay. I think I mentioned everything. Any questions? Okay, then let me repeat it really quick. You have an expert TA due this Friday. You'll have a quiz over the weekend. You have an expert TA due next week on Friday, and all of the expert TA final due date, December 19th. You'll have a quiz over that weekend as well. Your slides are due Friday, December 9th. Your video is due Tuesday, December 13th. Comments and your reflection essay are due December 16th. Yes.
Are we allowed to turn in the video on December 12th? Or when?
Yes.
When will it be?
when do I have this? I have it open on December 7th.
Oh,
So yeah, just feel free to get it done whenever you like. In fact, I think I have most things. No, I don't. The reflection essay I have due late. Whatever. Okay, but if everyone knows what they're doing for the next 2 weeks of your life, okay, excellent. Excellent. If that is good, we can talk about physics. Excellent. AC circuits. It's kind of a doozy. Chapter 15? Chapter 15. Okay, I'm going to share the screen. Okay. And that guy. Okay. Okay. AC circuits. Are any of y'all electrical engineers? Okay, you should probably not pay too much attention to this.
okay.
Um,
Thank you.
I'm
Is it gonna confuse me or what?
yeah. So basically, I'm gonna do the physicist approach, and we're not engineers.
It's like theory.
Yeah, like some ideas about AC circuits. You're gonna take a whole circuit analysis class. It's gonna be done so much better than this, and also very different than this. So yeah, you might get some ideas about how AC circuits works here, but it's a physicist's approach.
So don't explain that.
Yeah, it'd be like, this is what why physicists, no. No, my partner has one of his degrees is double E, and he's just like, no. That's sweet that you did that. It is, but he's an engineer and I'm a physicist, so if anyone's condescending, it's definitely me. Okay, but
Sorry, Ken.
Not about the phone. Everybody knows it. Everyone knows it, please.
anyway, you would think after 3 years you'd be on top of that. No. Okay, so but let's talk about AC. What does AC stand for? Alternating current. And how do you make an alternating current? How do you alternate your current? I like it. You make one of those generators that we talked about. If you remember, like the ones where you had a loop of wire and a magnet right here that made a magnetic field. And then you spun this thing and like you hook this up to, whatever, your light bulb, whatever you wanted to alternate a current through. And as it turned, the flux through that circle varied with the angular speed that it went through, and you ended up with a voltage where you had your Vmax sine omega t. Is that vaguely familiar?
Is that the same thing with the battery?
Yeah, it's like the opposite of the battery, where you had a motor and you kind of gave it a little twist to start off with, and then it kept kicking itself around. But yeah, so same thing, generator, you just turn the crank, and because the flux through the loop varies as the angular velocity, you end up with a voltage that looks like this, where omega is the angular frequency, 2 pi f. Okay, so that means 2 pi f. That means that the voltage you have doesn't just look like 6 volts, it looks like a sine wave. Really quick, do you guys know what frequency comes out of our walls?
Like the wall sounds like,
Yeah,
talking about like the voltage.
I'm talking about the frequency.
I know the voltage number.
What's a voltage?
The voltage is
120? Absolutely.
That's
And
just
we're
for
gonna-
America, right?
That's just for the US, yeah.
Yeah.
Yes. And just so you know, the frequency is 60 hertz.
Unless we
Oh,
have
is
the
it
industrial,
kids?
unless we have the industrial, but it's 64.
Yeah. And so this is kind of an important thing, right? Like, because the industrial plug, if you go to Europe, you need converters on your devices, right? You can't just take your device and plug it into the wall in Europe because they're running.
Little fly.
I don't know what they're running at Europe, but yeah,
He's right, I think.
I believe. Well, that's 240 volts is the industrial, like what you plug in your dryer into the wall. Yeah.
Strong.
Yeah, no, it's kind of massive.
I farted my over
Oh no.
there. It started smoking.
Yeah. Yeah. Okay. But yeah, so I see you guys are kind of understanding that, like, the frequency that's coming out of the wall, it matters for what you plug in, and in a very much different way than just what we've been doing in lab, where you hook up a light bulb to a battery, right? Like you can easily interchange your batteries. It increases your current, decreases your current, but it doesn't change the way your light bulb functions. Whereas with this AC stuff, it is going to change the way it functions.
So the frequency is half because it's going up and down.
So the frequency equals to 1 over the period. So if you were watching this like on an oscilloscope, it would go up and down and up and down and up and down. And the amount of time it takes to complete one whole pattern is the period. So if it takes half a second to go up and down, you have a period of 1/2 of a second, 0.5 seconds. Then your frequency is how the cycles per second, basically. So if your frequency is 1 over 0.5, you have a frequency of 2 hertz, which means you'll go up and down twice every second. Sound okay?
So it's just a coincidence that it's half of. Sorry.
Oh yeah, just a weird coincidence on that one. I actually don't know why, I don't know how that was set. Probably long ago by someone who didn't really care. Okay, let me ask you. Okay, so if the frequency coming out of the walls is 60 hertz, could you guys tell me the angular frequency coming out of the walls? Or just how to calculate the angular frequency? Yeah, 2 pi f. So we're kind of going to have two frequencies that we're talking about in this chapter. We're going to have just the frequency. And so when someone says, ask for the frequency, they want f. But then you have this thing, angular frequency, which is just 2 pi times that, which if f is 60, omega is 377. Thank you. 2 pi times 60, 376. And that will be in radians per second. And so when you see, and you'll see like 376 show up in the homework when they're saying that, they're just basing that off of the US electrical system. Okay. Most places, most textbooks are pretty good about saying angular frequency when they want omega. When you get out in the world, people are less good about that, and they expect you to just come at it from context. But do kind of be aware that there's those two different ways to say frequency. Okay. Next question. Looking at, so you guys are telling me correctly that 120 volts is coming out of the walls. And that's kind of a weird statement because the volts coming out of the walls look like this. They look like a sine wave. So when you say 120 volts, what do you really mean by that? Do you mean it's always 120 volts?
No.
Because it does that, right?
Max.
Yeah, so like one way to express that is say the maximum voltage is 120 volts. However, that's a little bit of a misnomer because that's not usually what we, that it oscillates one, but you're kind of, you want to say, hey, this oscillates, but you also just want to have a number to deal with. So this is where you get into different ways to talk about the value of something that changes. And note that the frequency here at 60 hertz, that means it bounces up and down 60 times every second. So it's really not useful to track the way it goes up and down because 60 hertz is pretty fast. Yeah.
When it's at the bottom and it has negative 120 volts, that's still
Yeah, so I've drawn a sine wave here that goes from positive 120 to negative 120 volts. Let me ask you, if I just wanted the average of this, so I have a sine wave goes from positive to negative 120. I ask you for the average value across one pattern. What are you going to tell me? Yeah, you're going to tell me 0, right? So if you have a sine wave, the average value of this is just going to be 0. And that's a bit irritating because an average value would be kind of nice when you have a varying something that changes over time. It'd be nice to have an average value, but clearly average doesn't work. And so let's talk about a root mean square value, where anytime you have some quantity that you need to take an average of, one way to take an average is this root mean square, where you take the square of something, then you take the mean or average of that square, and then to get back into your original dimensions, you take the square root of it. And so let's look at this sine wave right here. So if I have a function that looks like this, so my voltage with respect to time looks like that. And I want to take an average. If I just take a straight average, I get that 0. It's not useful. But what if I take a root mean square? So I square this whole thing. I get Vmax squared sine squared omega t. Now, a sine wave looks like that, goes from a positive value to a negative value. When I square that, am I still going to get the negative values? No, right? Because I squared it. Excellent. So a sine will go from, and let me just say sine squared here. So sine squared versus sine will look like this, where it goes up and down twice as often, because what you're doing is you're taking these minus negative peaks and you're putting them up there. But if I'm just looking at a sine squared, I'm going from 0 to 1, because the maximum value of a sine function is 1. 1 squared is 1. The minimum value is -1. -1 squared is 1. So this whole thing just exists between 0 and 1 now. Looking at that, I have a sine squared function. It goes between 0 and 1. What would the average value of this function be? 0.5. Absolutely. So the average value would just be the line down the middle, because this is very symmetric up and down. So it spends just as much time above that line as it does below it. So now when we take this and we take the average value over time, that sine squared just becomes a 1/2. So if I have squared and I take the average, I'm taking the average of this. Vmax squared, that's just a constant, so that's just going to stick around. And sine squared is going to give me a 1/2. Okay, I have squared, I have meaned. All I have to do now is take a square root of it to get it back into volts instead of volts squared that I have right now. So last step, I squared it, I averaged it, now I need to square root it. And so I'm square rooting Vmax squared times 1/2. Vmax squared just becomes Vmax, and 1/2 becomes 1/√2. Okay. And so let's take a minute and think about this, because this is going to come up. Was there anything particular about voltage than that in this derivation that we couldn't have applied to current or anything else as long as it varied like a sine wave? So if I had given you a current that looked like this, would you have, what would be different? I'm hoping you say not much. Because I would have squared everything, I would have gotten a sine squared. I would have taken the average of a sine squared and gotten a 1/2. And then I would have taken the square root of that and got 1/√2. So this RMS value is always going to be the maximum value divided by √2. And this is true as long as you have a sine wave.
So it doesn't matter if it's voltage or current?
Voltage or current or anything else that varies sinusoidally. And you're going to see this in like your various science classes. If you're looking at a sine wave, as long as it varies sinusoidally, you get this 1/√2.
Just sine, or could it be cosine?
It could be cosine as well. You get the same thing with a cosine. Now let me tell you that there are a bunch of other types of waves that you'll see, especially those electrical engineers out there. So like square waves, super common. Sawtooths, also super common. And so these sort of functions are going to give you different RMS values. You just have to figure it out based on the pattern that they give you. Okay. Okay, everyone pretty okay with that? We get the RMS versus the maximum. Okay, good. All right, so in the homework, you're going to see a lot of times they give you RMS values, other times they'll give you maximum values. Always just use that 1/√2 relationship to get back and forth between them. And basically, if you start in one type, just stick to that type. For example, let's do a real quick problem. Number 1, your homework says there's an RMS current, RMS of 12.5 amps. And they want to know the maximum current. Will the maximum current be more or less than 12.5 amps?
Less.
Less. Wait, what?
would it be to get it squared, Imax squared times?
So which is going to be bigger, IMAX or IRMS?
IR. Right. So to get it, you have to multiply the Imax squared with IMAX.
There we go. Okay, good. Yeah, so IRMS equals IMAX divided by root 2.
Yeah, I for a second I thought it was time for root 2.
No problem. I was just like, no, it's max.
It literally says max in the name.
Yeah. But yeah, just to get back and forth, that's all you do. You multiply or divide by root 2. So like in this case, IMAX is 17.7 amps versus the RMS of 12.5. Okay. Solid. Excellent. Then let's talk about how this is going to work. We are going to have circuits. And the circuits, the three things we have to work with, we have resistors, we have capacitors, and we have inductors. And so we're going to have a power source like the outlet coming out of the wall that is an AC power source. And so when you see a circle with a little wiggle inside of it, know that that is an AC source. Certain rules are still going, well, all of the rules are still going to apply. For example, if I have this resistor, inductor, and capacitor in series, that means the current has to be the same everywhere still. So series still means current is the same everywhere at the same time. So we're still like conserving charge. However, what we're going to find out is that voltage is going to act kind of weird, where when we do a Kirchhoff loop to go around this, we'll have the voltage of the source minus the voltage of the resistor minus the voltage of the capacitor minus the voltage of the inductor, and they're all going to need to add up to 0. But if you remember, we did LC circuits 2 weeks ago where the voltage would jump back and forth between the inductor and the capacitor. We're going to find that happens here, where this AC circuit, this AC source, will sometimes push current one way and sometimes push current the other way. So it wants to push current in different ways. And so voltage will build up and let off of the capacitor and build up and let off the inductor. And there'll be this big time varying kind of idea to it. Make sense? So while they all will add up to 0, they'll all have these weird time components where they're changing all the time. Does that kind of make sense? And what we're going to find is the current will have a sine wave. The voltages will all have sine waves, but they won't be right on top of each other. The current might be going up and down, and then the voltage of the capacitor might be doing something completely different at each point in time. Does that make sense? And so a big part of AC analysis is to see how in or out of phase your voltage is with your current. Where if you're in phase, the voltage and the current are all going up and down at the same time. But if you're out of phase, your voltage and your current might be going up and down at completely different times. Sound okay? Okay. So what we're going to do is we're going to look at each component separately. Then at the end of the day, we're just going to add them together. Sound good? Let's start with resistors because resistors are easy. So resistors. So I'm just going to have my source and a resistor. Okay. And what I'd like to do is I'd like to say if the voltage of my source is V max sine omega t. What does the voltage across the resistor look like? Now, when we had a capacitor and inductor, and we did like RC circuits and we did RL circuits, right? Let's look at RC circuits really quick because you're going to do that in the lab this week. It's going to be pretty awesome, by the way.
How long does the lab go?
Not that long. I wrote it, so it's like 7 maybe, like total, maybe 6 even.
Is it front and back 7 pages or?
Just front.
Okay, yeah, fine. This is
Yeah, it's pretty straightforward.
my wallet is.
If I hook up just a battery to a resistor and a capacitor, what can you tell me about the current with respect to time of that setup? If my capacitor is initially uncharged. No charge. So yeah, initially no charge on that capacitor. So when current tries to flow, the capacitor won't try to block it at first, right? So it initially starts at a pretty high current. But then as current flows, then charge starts to build up on that capacitor, that blocks the current, so your current goes down. Make sense?
I think so.
Yeah. And then the more the current gets blocked, the more the charge has to build up slower. So you get this dying off exponential. Kind of familiar? And so you get the time varying component because the capacitor can collect charge. Is that true of a resistor? So when I put current through a resistor, does it collect charge? Some no's. Hopefully no's, right? Like resistors don't collect charge, they don't hold energy, they just burn energy, right? At a constant rate. So we can say V equals IR. And this is really nice because the voltage of my resistor has to equal the voltage of my source because there's no time component for it to wiggle through. So whatever my source is doing, my resistor is just going to stay in phase with that. Another way to kind of look at this is if you do a Kirchhoff loop through here, the voltage of the source minus the voltage of the resistor have to add up to 0. So that means the voltage of the source has to equal the voltage of the resistor. And also, that means that that has to equal the current through the resistor times the resistance. Okay, now let's look at these two things. The voltage of the source now, and just my circuit with a source and a resistor, equals the current through the resistor times the value of the resistance. My source is V max sine omega t. My resistor has some resistance. So that means that my current has to have a sine omega t in it. Otherwise, the two sides of these equations couldn't be the same. Does that kind of make sense? And so that means that my current through this resistor is going to be some maximum value times sine omega t, where the maximum value, I max, will equal V max over R. Okay. I'm hoping this makes sense. And just to recap, I have an AC source hooked up to just a single resistor. the voltage of the source minus the voltage of the resistor has to add up to 0 because of Kirchhoff's loops. That means the voltage of the source has to equal the voltage of the resistor. And since V still equals IR, the voltage of the source has to equal the current through the resistor times the resistance. When you do that, you can see that the current has to have the same time variance, the same sine omega t as your source voltage does. That means that your resistor is in phase with the source. Okay, so let's draw a picture there. So I have time, I have my source voltage. It's going like this. I have, and it is V max sine omega t. And then I'm going to have my current, and I'm going to put it on the same axis even though it's not, like, doesn't have the same dimensions. So I through R, the current, I max sine omega t. Okay. And so when I say these things are in phase, what I'm saying is that they hit their maximums at the same time, they hit their minimums at the same time, they hit 0 at the same time. Whatever they're doing at the same time. So these two things are in phase. And what we are in particular going to be looking at is we're going to be looking at the source voltage and the current in the circuit. In this case, the current in the circuit is just the current through the resistor because that's the only thing in the circuit. So we can just say the current's in phase with the voltage. So current and voltage are in phase. Okay. Okay. So far that makes sense. Resistors are pretty straightforward. Since they're not like holding on to energy or letting go of energy, they're just in phase. I don't want to do that yet. I'm going to come back to that. Okay, next. Yeah, next thing. Let's look at capacitors next. I do have more capacitors. Good. Where's my capacitors? There. Okay. So resistors, straightforward. Resistors are in phase. Let's look at capacitors. So I'm going to hook up just a single voltage source to a single capacitor like that. Okay. My voltage source is still doing the time varying, so it's still a sine omega t right now. But I want to think about the voltage across the capacitor with respect to time, and I want to think about the current through the whole circuit with respect to time. Because as looking at this, so if I have a voltage and I put it across a capacitor, the first thing that's going to happen is the voltage across that capacitor is going to start increasing because it's building up charge. Sound okay? But then if I have an AC source, that voltage will flip immediately. This will start looking like a battery oriented in the opposite direction. And that will reverse this voltage that the capacitor was building up. So now instead of positive charges building up on one side, those positive charges are going to want to go to the other side. And so this capacitor will have this charge that's kind of lagging behind whatever the source voltage is doing. So the source voltage will be like, I'm oriented this way. And then the capacitor will start building up charge to oppose that. But then the source voltage will flip. And the capacitor will like, oh my gosh, let me try to build up charge in the other direction to follow you. And it'll keep doing this backwards and forwards. And so, while we can, and we will, set up our Kirchhoff loop, we'll kind of remember that this is very much a time-varying sort of Kirchhoff loop. It's not as straightforward as the resistor, where the resistor is just going to have whatever the same, is going to be doing the exact same thing as the source. So, what I'm going to be looking for here, I want to think about the voltage across the capacitor. I want to think about the current across the capacitor. Okay, so let's look hard at that. Where one thing I know is that the voltage across the capacitor will be equal to the charge on the capacitor divided by the capacitance, just from the definition of a capacitor. So voltage source equal minus Q over C equals 0. That means that if that the charge on my capacitor is equal to the voltage source times the capacitance, where the voltage source is V max sine omega t. Okay, so far so good? All right. But I didn't just want the current, I didn't just want the charge on the capacitor, I wanted the current through the capacitor. So if this is the charge on the capacitor, I'm sure you guys remember the way to get current is to take the time derivative of charge. Okay. So we are taking the time derivative of C V max sine omega t. Okay, that's C, that's the capacitance. Is that a constant or a variable?
You see?
The C, that's the capacitance. Is that a constant or a variable? Excellent. V max, constant or variable? V max.
Oh, constant. So that
Excellent. Yeah, and then sine omega t, that's really what we're taking a derivative of. Yeah, okay.
So we can WT or the omega t there.
Yeah, so we're going to like a ddt of sine omega t. And what is the derivative of sine?
Negative.
Negative,
Negative cosine. Or is it just?
it's just cosine. Just cosine. Okay, sorry. I have C V max, it's just cosine. And then we also have to do a chain rule because we've got to take the derivative of the inside. So the derivative of omega t is just omega. So I'm going to throw an extra omega there. Okie dokie. Let's put this all together in kind of a way that is useful to me. So the current through the capacitor, I want to say V max omega c cosine omega t. Now I'm going to take omega c and I'm going to create a variable called chi sub c. And it's going to be 1 over omega c. Okay, let's talk about this. This is the reactance. Reactance. So, and here's what a reactance is. It has units of ohms. What else has units of ohms? Yeah. So it acts kind of like a resistor in that we're going to say that the voltage across the capacitor equals the current times the reactance of the capacitor. So that should kind of remind you of V equals IR. And it kind of reacts to current. It tries to block current, basically. So this is how capacitors try to block current. It's just a value that we have of how capacitors block current. Now, we don't like saying resistance in this because it's not doing the same thing that a resistor does. Where a resistor, electrons go through it, and the resistors have friction in them, and so that burns up energy due to that friction. And so that's how resistors resist current. Capacitors don't resist current that way. They resist current like this, where they build up charge and block the current that way. And since they're doing like something that has like a different physical mechanism, we don't want to call it resistance. And so that's how we're coming up with this term reactance. Sound okay? Okay. But you can definitely just like base level say, you know, if you have more ohms, you're resisting current more. Let me ask you, if I have a really high frequency, so if my frequency is really high, does the reactance of my capacitor go up or down? It's 1 over omega c. No problem. But yeah, definitely down. So we're dividing by a larger number, we get a smaller number. And what that's telling you is capacitors don't block high frequencies. Okay. So if you run a high frequency across a capacitor, it'll act almost as if the capacitor isn't there. It'll just act like a wire. Because this idea that if you flip your voltage often enough, your capacitor won't have time to build up any charge, and so it won't have the ability to block any current. Make sense? Okay. What if you have a low frequency? So if you have a really low frequency, your reactance should go up, right? That means if you put a low frequency across your capacitor, it will block a lot of the current going through. And what you should kind of be thinking about here is you should kind of be thinking about high and low pass filters, where if you're running a bunch of different frequencies through a circuit and you only want the high frequencies to come through, you run it across a capacitor, because the capacitor will block anything with a low frequency, but it can't do anything with the high frequency, so it'll just let the high frequencies pass. Does that make sense? Okay, cool, excellent. And again, I'd like to kind of note that this stuff coming out of the wall, so like if you have a power supply designed for 60 hertz, it's going to set its capacitors so it'll have the correct resistance at 60 hertz. But it won't have the correct resistance at 80 hertz or 100 hertz, because capacitors react differently to different frequencies. Everyone happy there? Okay, so magnitudes. I have this reactance, it's in ohms. And then let me go to here and note if this is omega c, my reactance is 1 over omega c. What I'm going to get here is the current in the capacitor is V max over chi c times the cosine omega t. So we just, right here, we combine these things. I got V max over chi c. Okay, and hopefully that kind of gets you kind of to this point where V max over something in ohms, that's going to give you a current. Next thing to look at is to look at the time dependence. So we have the source voltage coming through with a Vmax sine omega t. So let's draw a sine omega t here. So there's my source voltage. Then we have the current through the capacitor coming through as a cosine omega t. So current through the capacitor, cosine omega t. Now it has the same frequency, so it'll complete a pattern in the same amount of time. So if it starts right there, it'll be done right there. Same amount of time to complete this pattern. But it's definitely out of phase with the voltage. So there's the current, there's the voltage. They are not in phase. In fact, they're out of phase by pi by 2 or 90 degrees rads, right? Because your sines and cosines are out of phase by 90 degrees. Is that okay? Okay, good. And then what I kind of like you guys to see is that this voltage is lagging the current. And this one's always hard for me to see. But whatever the voltage is doing, the current had done a second earlier. So this is the earlier time. Earlier, this is the later time. So the current hits its peak, a second later the voltage hits the peak. The current hits 0, a second later the voltage hits 0. So the voltage is lagging behind the current. Make sense?
Isn't the voltage current kind of the same though? So how is it like?
I'm so glad you asked. So looking at this picture, my battery has a voltage, right? But the current through the circuit isn't always the same. Yeah, because, and this is a really big point, so I'm going to say it a lot. So the current through the circuit in this RC circuit is not even, I wouldn't even call it in phase because it doesn't even follow the same pattern. The current in the circuit is not the same as the voltage to the battery. If I do the voltage of the battery, I get just a flat line. I draw my current through the circuit, I get this exponential. Okay, so here the voltage just coming out of my source doesn't do the same thing as the current through my circuit is doing. Now, nicely enough, they do follow the same pattern, because it would be really irritating if one was a sinusoid and another was an exponential. But they don't do the same thing at the same time. Okay. Now, okay, so they're out of phase, pi by 2 radians, where the current, the voltage lags current. Okay. Next thing, I'm hoping you see that drawing these sinusoids is actually not easy and not particularly illuminating. Maybe, yes, no. And trust me, I'm about to like throw a resistor and an inductor on top of that as well. This is not the best way to visually understand what's going on in the circuit. And so this is where we're going to come up with phase diagrams. Okay, phase diagram. Where what we're going to do is we're going to represent a sine or a cosine. So like our IC is the current through the capacitor, I max cosine omega t. Like that. We're going to represent this as an I max times e to the I omega t. Is that all right? Where if I have this particular thing, I need it in green. If I have this particular thing, it would really be this I max this would be some angle, and this thing would be spinning around at the angular frequency omega, so that after some amount of time, the angle it makes, whatever angle it is, would be the angular velocity times the amount of time it was going for. Yeah?
What's the I for? It's for the E to the I omega t.
Oh, this is why electrical engineers are better than physicists here. This is the square root of -1, not the same as current, which is why electrical engineers use J for the square root of -1.
It's just the imaginary number. Right?
Yeah, just the imaginary number.
I thought it was a variable. So that's
Yeah, no, it's not. This is why electrical engineers do it differently. They're right to do it differently.
What was the point of value? Like it's to get like a negative.
The point, it's so you can have like a real and an imaginary axis where cosine plus I sine, where this is the real axis and this is the imaginary axis. And it's really just a way to like shoehorn an extra dimension into your equations that you don't really have, but it's nice. Okay, what am I doing here? Okay, so I have this vector. It goes around. So so basically you've set up your circuit. So I've plugged a capacitor into the wall, and if I was measuring and if I put a little ammeter in my circuit, it would be measuring the current going up and down and up and down. Or if I displayed it like this, it would you just see this line spinning around in a circle. Make sense? Where if you also measured the voltage across that source, you would say, hey, the voltage lags the current by 90 degrees. And so your voltage, V of the source, would be like that, and it would be spinning around at the same speed, always 90 degrees away from your current. Does that make sense? Okay, so you've got your current, you've got your source, you hooked up your ammeter and your voltmeter, you're watching these things spinning. And one thing you might realize is that it's not super useful to watch these things spin. It's more useful just to say, you know what I really need to know is how the voltage and how the voltage and the current are related. I don't need to know that what they are at any particular time, because they're going around 60 times per second. So knowing what they're doing at any like 1.123 seconds, that's not very useful. But how in or out of phase they are, that is useful. So instead of trying to picture this thing spinning around, what you do is you just choose a time. And so generally what you do is you say, okay, I'm going to set current to go that way. Now, in my mind, I know that it's really spinning. as it goes around. But what I really care about is that the voltage across that capacitor is 90 degrees behind the current through my circuit. Okay? This is a phase diagram. Okay, so a few things. One, I've been saying this is the current through the circuit. I'm sorry, I've been saying that's the current through the capacitor. Since in this setup that I did, I just have a capacitor and a source. That's the current through the whole circuit, because the current has to be the same at all points because they're in series, right? So that rule still applies. So the current's the same everywhere. So when I have the current, that's just the current of the circuit. The voltage is the voltage through the capacitor. So in this picture, I have the current through the circuit and the voltage through the capacitor, where the voltage of the capacitor lags by 90 degrees. This is the orientation that we're going to use for all our phase diagrams from now on. The current goes on the x-axis and the capacitor goes down. Okay, this is good. This is very good. If that works, let's talk about inductors. Where's my resistors, currents, inductors? I'm sorry, I think I've got that. Where do I start inductors, guys? I got resistors. There we go, inductance. Sorry. Okay, inductors. So we're going to do something really similar with inductors. We want the voltage of the inductor, and we want how the current in the circuit works. So let's start the same way. Let's start the same way. Let's hook up our source to an inductor. So basically, we just have the simplest possible AC inductor circuit. Where when we do our Kirchhoff loop, we have the voltage of the source minus the voltage across the inductor needs to add up to 0. Where, if we remember from 2 weeks ago, voltage across inductors equals negative L di dt. Vaguely familiar? Okay, cool. And we can just substitute this in. So our source voltage minus, I'm gonna play a little fast and loose with my minus signs. I'll catch you up at the end of the day. That needs to add up to 0. The minus sign, this minus sign and this minus sign are the same, so I don't want to add them together. They'd be redundant if I did that, and I'd screw up my answer. Okay, which means that my source voltage equals L di dt. Now again, I'm looking for that I right there, and I know that my source voltage is Vmax sine omega t, like that. So let's start isolating the I. So I'll divide both sides by L. di dt Vmax over L sine omega t. And then I'm going to take the time integral. Well, that's not really what I'm going to. Then I'm going to multiply both sides by dt. And so I'll have di equals V max over L sine omega t dt. And I'm integrating both sides of that. Sound okay? Let me do this integral, and then that's where we're going to stop. So the integral of di, just I. The integral V max over L. So V max and L, are those constants or variables? Constants, excellent. And what is the, and then we're going to do a little U substitution here, where omega t equals U. So du equals omega dt. So when I plug in this U there, I need to have a du over omega right there. And omega, that's just the angular frequency, so it's going to come outside. And we're integrating sine. And what is the integral of sine? Cosine, and it's a negative cosine, right? Because you're going the other way. Excuse me. And then I can plug back in omega t right there. Okay. Here's where I'm going to stop. Please remind me on Thursday, this is where I stopped. We need to talk about the reactants, and we need to talk about the phase of this current versus the voltage. Okay. Any questions? Lots of questions because you can see where it's going to go, and yeah.
I was wondering why it was 1 over omega, and everyone's view. That's how you got it.
Yeah, exactly. And that's going to be important because now we're gonna have a reactance, and it's going to have a different interaction than the capacitor did. Online people, are you guys kind of okay?